Right, so my name is Mateja Jamnik, and I work in the Department of Computer Science and Technology at the University of Cambridge. And I'm going to talk to you about a project that, or about a piece of work, a volume of work that I'm very passionate about, and that I work with. It's obviously not just my work, but it's a piece of work from a whole team of people named on this slide in particular. And the problem revolves around, we are interacting with these smart tools all the time, but we end up having to adapt to these tools. So imagine that you are using a sat nav and are you trying to get from A to B. And the sat nav typically will tell you, in 150 meters, turn right. In 200 meters, turn left. You have reached your destination. So, but if I'm familiar with the place, I would much rather have a sat nav telling me in 150 meters, or rather 150 meters at the grocery store, turn left. And then when you get to the cinema, turn right, and then you'll get to your place. So I would like these AI tools to be able to adapt to me and the way that to my expertise. And so it's a question of representation, and you can see that it's applicable across very many different domains and problem domains and areas. It's a very generic problem, but it's also a very big open problem from the theoretical point of view. How do we choose a representation that is appropriate? So this is the talk that I'm going to, or the work that I'm going to present to you here now is about this question. So this is just the structure of the talk. I'll start by giving you a few examples and asking you to try to infer things with me. And then I'll introduce a language of how we talk about representations, and then the algorithm of how we select representations, and then how do we personalize this framework and mechanism for a particular user, and then I'll indicate some ongoing work and future directions. So let me start with the vision. So I give you an example of an AI system like a sat nav that is talking to you, but there's many, many more. What we would like is that these systems would adapt to us, not the other way around. But the problem is that most of them operate just with a single, usually machine-oriented representation that we have to adapt to. So why is changing representation and finding an appropriate one for a task or a problem that we have at hand important? Well, there's a huge amount of literature out there which is justifying or giving you reasons or finding you evidence why this is why it's positive and why it's enabling. So first of all, it gives us new insights and new understandings into the task or the problem that we're trying to address. And also it enables us to personalize these tools that we are interacting with on the daily basis. In terms of the literature, you probably have heard of a famous mathematician, Polya, and he basically said, if you find the right representation for your problem, then solving your problem becomes trivial. In cognitive psychology, we have, people have claimed that finding the right representation, such as, for example, diagrams, they are worth 10,000 words. In cognitive science, experiments have been carried out which show that finding the right representation, changing representation dramatically improved the performance of the people who were using that representation and solving a task. And in philosophy, the concept of free rights has been around for a long time being studied, which basically says a representation is a good one if it's got a lot of free rights, where you get insights for free. You don't have to infer them. Just by inspecting the representation, you get new insights. So I hope you would agree with me that changing representation is beneficial, is important, is enabling us to reach these goals. So in this piece of work, we are trying to build a tool that will help us choose a representation that is suitable not just for the task that we are given, but also for the person who is trying to accomplish that task. So let me start with giving you a practical example. So here is a medical problem, and the problem says that 4% of the population has a disease D. And for those who have the disease, a test T is accurate 95% of the time. And for those who do not have the disease, the test is accurate 90% of the time. Now, these tests are expensive. And if you do take a test and it comes out positive, what's the probability that you have the disease? Okay, kind of topical at the moment as well, isn't it? So how can we go about this? So first of all, I gave you the problem represented in the natural language representation, but here is another way of going about it that probably mathematicians or logicians would go about it, or experts. So it's called the Bayesian approach because we are representing the problem using a formal conditional probability. So how would I go about it? Well, we have that the 4% of the population has the disease D. So I represent here this with the probability of D is 0.04. Then we have for those who have a disease, the test is 95% accurate. Then we have that if you don't have a disease, then the test is 90% accurate. And now our task is to find that if you take a test, what's the probability that you have a disease? So this is how we would represent this problem using the Bayesian approach. And the solution under this approach goes like this. So we have a few facts that we know in this particular representation. So here we have the Bayesian law, and then we have various other probability laws. And you don't need to understand the details of these formulae, but it's basically just given here to see that you have these axioms. And then when you derive, you start from your problem and you use these axioms to derive your solution. So I'm using 1 and 2, 3, 5 and 4. And then finally, I come to the point where I can apply my assumptions. And it turns out that the probability that you have a disease if you test positive is 28%. Okay, so let me ask you, I'm going to carry out a little poll here. And let me ask you, launch the poll. Do you understand this Bayesian solution? So the question is, I hope you see it and I hope you will participate. So do you understand what it's about? And do you understand the intuition behind why the solution is correct and so on? Oh, I can see we have quite a few mathematicians. I guess we're all in computer science, so I guess we're a little bit biased here. Still got figures going up. I'll give you a few more seconds. I'll ask you another question later on with another representation. So, okay, are we stabilizing here? Yes, I think so. So I'm going to end the poll now. And we have shared the results, and you will see that 77% of you understand the solution and 23% of you do not understand this solution. But fear not, I have another poll for you, or another representation that I'm going to show you for this problem. So thank you very much for participating in this poll. Let me write down. So 77% said yes. We might do a little recce in the end. Okay, so let's look at the same problem and use another representation that I call areas. So we represent the population as this square of the entire population of 1, and I take a column out of 4% of the population that has this disease, and 95% of them for them the test is accurate. So these are people who have the disease and have taken the test and it was positive. And now for those who do not have a disease, the test is 90%. So you can see here, this is an accurate 90% of those who don't have a disease. Unfortunately, those who don't have a disease, 10% will get a false positive here, which is just this area here. So how do we find out if you take a test? So that people who have taken a test and it came out positive are all the great people, but the people who have a disease are only the ones that are striped. So the solution is, what's the probability that you have a disease if you've taken a test, is this, the proportion, the ratio between this stripy area and all of this gray area, right? And it turns out it's obviously the results should be the same. Okay, so I've used areas here to convey the notion of the solution. So here is my second poll. Do you understand this area solution? Let me launch it. Question 2. Oh, where's my, there we go. I hope you can see it. And let's see how well we do with this one, how well you understood. So the question is really, do you have an intuition of why this is a solution and why it's correct? Oh, it's working like a gem. It's going exactly how I was hoping it would go. So a few more seconds. Oh, numbers going up still. Okay, I'm going to pause here. Last chance. And end the poll and share results. And we have 85% of you understood this solution. And still 15% did not. Okay, so that's kind of what I was hoping for, that we will get. Okay, so I've showed you two different actually three, because there's also the natural language representation, but there are also many other representations that I could have used. So some of you might have come across contingency tables, where then the solution is that you have to find the ratio between these two cells. So you have to fill out the cells, or probability trees, which is what our kids are, I think, taught mostly about probability at school, except it turns out that if you represent this problem with probability trees, is quite tricky to then compute what this X is supposed to be, because you have to use various laws and so on. So you can appreciate that you know, some representations are better than others, and it really depends on very many different things. So why would we want to be looking between these representations? Well, how would we be choosing? So, well, they make different things evident depending on which representation you choose. They require different types and kinds of knowledge. They allow us to do different kinds of manipulations, and ultimately, and very importantly, different people think differently, and different people have different levels of expertise. So if you have a 10-year-old kid, or if you have a first-year undergraduate student, you would probably use a different type of representations. Okay, so this is my last poll, and the question here is, which representation do you prefer? And I'm only going to give you, because I went through the details, the two that you've seen. So the Bayesian representation or the areas representation. So hopefully these results will be consistent with how well you understood the solution or the representation of the problem. Very nice. Okay, a few more seconds. Excellent. I'm going to stop now. And we have that 71, let me show the results. 71% of you prefer the area solution, and 29% of you prefer the more formal Bayesian solution and representation. Okay, that's excellent. And I will, by the end of this talk, I'll tell you how consistent this is with the rest of the population, or at least the ones that we've tested. Okay, so so we want to basically build this kind of framework, which we call rep to rep, where we are able to even talk about these kinds of issues, so where we can even talk about describing the representations and then making some analysis and algorithms that are going to enable us to select the appropriate representation. And I should point out that, you know, even talking about representations is a very big open problem in artificial intelligence or in general. And so our approach is that we would like to describe representations, but do not have the requirement to formalize them in the logical sense, these representational systems. So we want to describe them in sufficient detail that they're going to, and that it's going to enable us to make effective selections and choices when we're selecting our representation. So I should point out that we're not devising a complete formal theory of knowledge or of all representations, because that's completely untractable. And we are just kind of taking, if you like, a pragmatic approach, which is going to enable us to do something useful. And so this framework needs to consist of descriptions or the language, vocabulary for talking about the representations and problems. And it needs to have an algorithm which is going to analyze the representations and then select them. And so this algorithm is based on two concepts: informational suitability, which means what can the representation do and how well can it describe the problem. And then cognitive costs, which is basically the cognitive effort that is required of a human if they use that representation, and how does it align this with the individual levels of expertise for that particular user. So let me start by talking about the language, the vocabulary of representations. So obviously we will use, we will describe the representations in terms of symbols they use, inferences that they enable us to do, and the knowledge that they encode. And the first part is, we call it grammatical, and consists of primitives and types and patterns. And the other one is inferential, which is about the facts and laws, so encoding knowledge, and about tactics, so various manipulations, what we can do with that representational system. And so for each of the representations and problems, we want to encode them in this kind of language. So going back to my examples of Bayesian and area representation, how would that look in our language? Well, it would look a little bit or very much like this, but with a lot more detail. So what can we notice here? You can see that we have here the primitive probability, which coincides with that. What else do we see? We have Bayesian theorem here, which was one of the rules which we have here. And then we have these manipulations, so we can rewrite and so on, which is exactly what I did for the solution. And in areas, we have what? The region here, which corresponds, we have 4 of them here in this solution. And then we have various other things. We can measure areas and so on. So it's a language that describes these representations. And I'll show you and convince you how this is sufficient then to analyze these representations. So similarly for problems, these are they are described using this language in a similar way that the representational systems are, but they have additional things. So they have features that are problem specific. For example, one thing is some very observant amongst you will have noticed that my problem has given me a very funny fact, which I did not need to use in any of my solutions. Basically, the tests T are really expensive, and that's not an important component of the representation of this problem. So the descriptions of problems come also with this additional attribute, which is called importance. And obviously, the probability component primitive is of very high importance, whereas the tests are expensive is not. So we encode this in the concept of importance. Okay, so now how do we go about selecting and analyzing different candidate representations? So we can describe first, we describe the representations and problems, and I've showed you the language to do so. The next step is that we need to find a candidate alternative representation, or if we have a suite of them, we need to find an analogy between the problem and the candidate representation. And that's done with we do this with the concept of correspondences. Then we need to evaluate if this candidate representation can actually represent my problem, and we call this informational suitability. Then we need to bring in the user and see, is this candidate representation actually suitable for my human user, and we encode this with cognitive costs. So going back to my example about Bayesian representation and area representation, correspondences are encoded in these triplets where C is the set of all correspondences between two representations, and Q is a component that comes from this first representation, so in this case Bayesian representation, and R is the second component, which comes from the is a component from the second representation, in our case from the area representation. And then S is a parameter which basically encodes how strong is the relationship between these components. So here the relationship between probability and region is clearly very strong. So I assign it the strength of 1, and here is my first correspondence that is part of my set of correspondences. Here's another one. So the law of total probability very much corresponds to the law of adding up the areas. And so it's very important. So I assign it high importance here. And here's my next correspondence. So now that I've identified my candidate analogous representation, how do I estimate how well it can encode my entire problem? So again, this looks perhaps scary, but what I want you to take away from this is, so IS is my informational suitability, and my first representation is, for example, Bayesian, and the component, this Q, comes from there. So this is a primitive PR. Then this is my second representation, which is the area candidate representation, let's say, and the R is coming from there. And here is my S, which is the strength of their relationship and the importance of how important, in fact, this primitive PR is. And obviously, in this case, it's very important, but the fact that if this was tests are expensive, this would not be important at all for given this problem. So I will basically walk over the set of all correspondences and add up these quotients, and that's how I get to the measure of informational suitability. Okay, so we have the vocabulary. Now we have introduced the concept of correspondences. We have the informational suitability. Now what about the user? So how do we personalize all of this? How do we find that this is suitable for a human user? Well, as I said earlier, we use cognitive costs. So we use the concept of cognitive properties to characterize what is the load that the representation might place on a particular person. So basically, we want to analyze these cognitive properties and compute their cognitive cost. But where do they come from, these cognitive properties? Well, here is some systematization of cognitive properties. It comes from the literature, and we have organized them in a particular way, and we have picked, again, you don't need to know all the details, I'll just pick out a few highlights in a second. And we organize them according to the cognitive processes that they demand of you, and then about their granularity. Are they very atomic, or are they very composite, and so on. So again, these come from the literature. We just put them together, we systematize them, and we organize them. So for example, the branching factor would very much affect the working memory load that this representation would place on the user. If the user has poor problem-solving heuristics, but the inference type is very complex, then obviously this would not be a good match, and this inference type would carry a very heavy load for that particular user. If the concepts were difficult to map because they are complex, then that information that they encode would be difficult to access for a particular user. So again, this would place a higher cognitive load for the particular user, depending again on their level of expertise. Now, how do we find out what kind of load would be for a particular user? Well, for each one of these cognitive properties, we could run user profiling tests, and indeed we did run some of them, in particular for quantity scales, and we asked them, there are specific tests that you can do in order to test that level of expertise or ability in your particular user. And so we've done a few of them, but not all of them yet. And they've informed our prototype, if you like, or our proof of concept of how to account for cognitive costs. So here is the formula. Again, you don't need to know all the details, but I'll just highlight a few main ideas. So this U is my user. These P's are my properties that you saw 9 of them in my table. Every property has a cost associated with it. So for example, the working load memory or the branching factor would be much more important than, say, the number of tokens or the expression complexity necessary, for example, as a property. So they carry different costs. And then here is the cost, the cognitive load that is being computed for that particular user. So whether they're a novice, whether they are an average user, or whether they're an expert, or any level of granularity in between. So this is how we compute our cognitive costs. So I have the language, the vocabulary, I have the way of making analogies, I have a way of finding whether I can actually talk about my problem using candidate representation, and I have a way of assessing whether my candidate representation is the right one for a particular person who's going to use it. So our algorithm, we have run it on many on examples, and so how well did we do? How do we even assess if this choice is good? So what we did was we ran, well, we thought, if an expert analyst, a human expert analyst, would rank these representation in this way, a similar way that our algorithm would be, then we're happy. I think that then we would consider this to be a success. So we indeed carried out empirical studies where we used human expert analysts to rank representations. In fact, I'm here showing you only 4, but we've used more than that. And then we ran our algorithm, and you will see that Bayesian representation came on top in terms of informational suitability, which is how well can it represent a problem. So it's a very precise way of representing a problem. And natural language expectedly came last. And in between, we have a little bit of disagreement between, but on average, I think that we were happy with this. And as we refine our measures of importance and the strength, cognitive cost, I think these things will, results will improve further. And we did the same thing about for the cognitive costs, and we asked the human expert analysts how appropriate would be a representation for an expert, how appropriate would be for an average person and for a novice. And again, you will see that our results very much agree, especially what comes top and what comes bottom. So let me see. So here, the smaller the value, the better, whereas here, the higher the value, the better. So for the going back to our little poll that we did in the beginning, 71% of you rated Bayesian representation, rated areas representation above Bayesian representation. So that would place you here somewhere. Kind of agree. Similar, yeah, very close. And so are you experts, average, or novices? I would probably say experts. Okay, so And so this give us, there was statistical significance in these results. And of course, since we've only done the profiling test for the quantity scales for one of the properties, we need to do a lot more. So the question is now, how do we combine informational suitability and cognitive measures? So that really depends on what we're trying to do. So if you're in a problem-solving situation, then the user is very important. So you would definitely place more importance on the cognitive costs. But if you're in a tutoring situation, then the informational suitability is more important, because you might want to expose a new concept. And because it's unfamiliar, it will probably carry a heavy cognitive load cost for the users, and that's intentional. So it depends how we want to combine these. So let me conclude by saying that we have devised a language or vocabulary for talking about representations and methods for computing their suitability. And we see that this can be applied in many different domains. And we are operationalizing all of this, implementing additional stuff, additional profiling tests. We're carrying out empirical studies, but most importantly, we are applying this, or wanting to apply, this is the next step, apply to the AI tutoring systems for problem solving, so that the tutoring system will adapt to the student, or will adapt to what the teacher is trying to, what concept the teacher is trying to convey. And more generally, if we go back to our GPS or sat-nav example from the start, when the system will understand that you are a local, it might want to give you directions in terms of your local landmarks. But if you're a tourist in a new city, then probably giving you directions in terms of meters is appropriate. Thank you very much for listening. And if you have any questions, I'm very happy to hear them.